This is 10-5, colliding blocks and different initial speeds. Now, there are some kind of cringy parts of this FRQ, but there are also some good parts. So I'm going to use it, and I'll explain as best I can the parts that are, like I said, kind of cringy. So we've got an experiment here, case 1. At time t1, block A is sliding to the right along a horizontal surface towards identical block B, which is at rest. All of these words are important. At time t2, block A collides elastically, okay? So over on my little scratch paper, I'm writing elastic collision. And I'm thinking, okay, kinetic energy is conserved. That's all I know for now. At time t3, the right block of side B, go back to the second bullet point. Block A comes to rest. So that elastic collision means that if block B was at rest and block A comes to rest, block B now has the same initial velocity as block A because kinetic energy is conserved. Sorry about that. At time t3, the right side of block B reaches an ideal horizontal spring with negligible mass and spring constant K1. The spring is initially relaxed, uncompressed length, and fixed to a wall. At time t4, the spring is compressed to maximum distance, d1, and block B is instantaneously at rest. Now, if we went on, of course, block B would shoot out towards the left and hit block A, but we don't care about that. Assuming there's negligible friction between each block and the surface for parts A through D, consider the system containing block A, block B, and the spring. Okay, that's going in my notes too. System is both blocks plus spring. Okay, what does that mean? That means if I'm talking about conservation of mechanical energy, I can use K and I can use US because the spring's in my system. Gravity is not really playing a role in this problem. Okay, part A. Indicate whether the linear momentum of the two-block spring system is constant or not during the interval from time t1 to immediately before t2. So during t1, this interval, block A is moving. There really isn't even a collision yet. So the criteria for momentum to be conserved is no net forces. So that's absolutely the case here. So the answer is yes. Yeah, it's constant. Okay, so 1 point for saying it's constant and having an explanation, and 1 point for that explanation talking about no net external forces, right? Part B, indicate whether the mechanical energy of the system is constant between T1 to T3. All right, now during T1 to T3, we've got the collision happening, but we have been told, and you've written down, that it is an elastic collision. So we get a point for saying mechanical energy is conserved, and some attempt at an explanation, okay? Even these yes-no questions always require an explanation. So just saying yes or no is not going to get you anywhere. Even if your explanation is wrong, you can still often get that point for trying to explain, right? But then 1 point for a correct explanation, like that mechanical energy, kinetic energy is conserved in an elastic collision. All right. Now part C. Indicate whether the linear momentum of the two-block spring system is constant or not during the interval from T3 to T4. Now this for me was the part that was a little bit cringy because between T3 and T4, the block is compressing the spring, okay? Now the spring is an ideal spring, which means it's massless, and you really don't deal with the length of the spring. So the answer here is that the spring is exerting a force on block B, so momentum is not conserved. Now, I know we already said that the spring was part of the system, but that really only works for the energy portion of this conversation. So you could say, well, the spring is part of the system, and so that's not an external force. But the fact is that the spring, we don't think of the spring as having momentum because an ideal spring has no mass. So if the spring can't have momentum, then that system lost momentum because block B lost momentum. And why? Well, because the spring exerted the force. So when we talk about the spring here, we definitely can talk about it as being in the system when we talk about energy, but we can't really talk about that force being internal because the spring can't have momentum. So I totally understand if that doesn't make a whole lot of sense to you. And we didn't talk a great deal about it because it's a weird niche corner of this conversation, but you get a point for saying it's not constant and trying to explain why, and then one for saying that there's a net external force. My guess is that if you say momentum is conserved because there's no external forces because the spring is inside the system, you might even get that 1 out of 2 points. I'm not entirely sure. But I think if I were grading, I would give that point. That was the difficult part of this, okay? So on to part D, indicate whether the mechanical energy is constant or not. The mechanical energy is constant because now we can consider the spring force as being internal, okay? So we have no net external force, all right? So I know that's a little confusing, but just to review, when you're talking about momentum, you can't really use the spring as part of the system, but when you're talking about energy, you can. So 2 points for that one. And honestly, even if that part C was difficult for you, I think parts A, B, and D were definitely gettable, and that's 6 out of the 8 points. So again, partial credit, partial credit, partial credit. All right, now, case 2, of course, you knew this was coming. The identical setup to case 1, but the speed of block A before colliding with B is greater than in case 1. Block A again becomes initially to rest, and we've got an elastic collision again. Now we've got the spring compressing another distance, D2. How does that new spring compression distance compare? Is D2 greater than, equal to, or less than? That's part E, and then part F is explain. So the answer then is D2 is greater than D1. So you get a point for that, just for getting the right answer, and that's the point for part E. Now there's 2 points, that you can get for part F. And here's what I said, okay? That means I said that block A will have more momentum than in case 1 before hitting block B. Since it's an elastic collision, well, not even that. Conservation of momentum says that block A's momentum is transferred to block B. Since it's an elastic collision and block A comes to a stop, all of its momentum is given to block B. So block B now has a greater momentum. Since block B has the same mass, it will have a larger velocity and therefore a larger kinetic energy than before. That means it has more kinetic energy with which to compress the spring. More energy is going to compress the spring a larger distance, and therefore that D2 will increase, right? That's the answer. It's almost a little paragraphy, but this isn't a paragraph response. It's just our qualitative answer there. So here's what the rubric says. 1 point for saying that block A transfers all of its momentum to block B, and that block B has more momentum than before. 1 point for saying a greater kinetic energy means a larger spring potential energy, which means a larger, a larger distance compressed. So 1 point for getting the greater than, D2 is greater than D1 in part E, and 2 points for part G. Now let's get some 2 equations, and this is one thing that they sometimes do in a QQT. I think it's the first one we've seen. Equation 1 says, all right, D is equal to some constant times the mass divided by VK. Equation 2 says, no, the distance is equal to this other constant, M over K, and then we've got the V outside the rad sign. In the 2 equations, they're constants. They're just different constants. So G says, without deriving the correct equation or anything else, explain which equation better supports your explanation for the distance in part F. Now, what did we say in part F? Well, we really said it in part E, what we said was that, first of all, what's the only thing that is changing in this equation? The mass of the block is the same, the velocity is the same, the spring constant is the same. The thing that's changing in case 1 and case 2 is the velocity. In case 1 has a smaller velocity, in case 2 it has a larger velocity. So what we want is a formula, and what we said is that a larger velocity of block A means a larger compression distance. And so in this formula, a larger velocity being in the denominator means this is going to be smaller. Over here, a larger velocity saying this is in the numerator means this is going to be bigger. Sorry for that awkward pause. So the answer is equation 2, all right? So you get a point for saying equation 2 and addressing a functional dependence by somehow talking about how velocity is in the numerator, and then 1 point for relating the distance compressed correctly to the velocity. All right, somehow this never-ending question is going on. Part H. The graph above shows displacement of time for the blocks while B is in contact with the spring. The solid line corresponds to either case 1 or case 2, while the dashed line corresponds to the other case. All right, another good question. Does the dashed line curve correspond to case 1, the slower block, or case 2, the faster block? And explain your reasoning. So the dashed line shows a smaller compression distance. The solid line shows a greater compression distance. So we had a smaller compression distance because we're addressing the dashed line, okay? The dashed line means a lesser compression, so that's the slower block, case 1. So the answer is case 1. So you get 1 point for saying case 1 plus attempting a justification, 1 point for addressing the amplitude and the energy, which is what I said. A smaller amplitude means a smaller displacement. That took case with the smaller block. Or they said you could take, displacement versus time. What can we do? We can look at the slope of the line, which is the velocity of the block, right? And it's going faster on the dotted line because that slope is bigger. I actually didn't think about that, but that's a pretty clever way of doing that. The solid line, the slope is larger, which means the block is moving faster. Well, that's case 2. But they ask for the dashed line, so that's case 1. So that's it for the Unit 4 QQTs. I hope they helped.